So in this problem, I'm looking at the spinner being spun more than one time. Now it's being spun twice. And I have a specific order how I want it spun, where I want it red, then I want it yellow. So when I think about how I write my probability, that is the probability of red and yellow. And that's the specific order I want it. So I think about these are independent. So I can do the probability of having the red times the probability of having the yellow, which would be 1/8 times 3/8, which would mean that that probability would be 3/64. Now the question is, what's the difference between that keyword of having then versus just saying and a yellow? So remove that word then. Well, what that means is that the order doesn't matter. So that would mean that my probability could be red and yellow, or yellow and red, as long as the two are chosen. And what that ends up doing then is I've got the probability of red times the probability of yellow plus the probability of yellow times the probability of red. So what it ends up doing in this case is this becomes 1/8 times 3/8 plus 3/8 times 1/8. So I get 3/64 plus 3/64, which means that I've now got 6/64 chance of this happening. So by not having to care about order, I double the number of opportunities that could potentially get me this specific situation. So order matters, and order impacts our probability. So that is something to pay attention to. So that's why we get to this bear problem, where we're looking at the idea of having two bins, and we have an option as to which game we want to play, where we pull a bear out of each of those bins and we can win some money. So if I start with option A, I'm going to pull a black bear from each bin. So that would be the probability of black in 1 and black in 2. And that's the only way I can do this. So, and they're independent bins, so I know that this would be the probability of black in 1 times the probability that I got a black in the second one. So this is 2/6 times 6/8, which is 2/8, which is 1/4. Now with B, I'm pulling a light bear from each bin, so that's the probability of a light bear on the first one and a light bear on the second one. So since they're independent, I know I'll just multiply the probabilities of each of these separately. So I have a 4/6 chance in the first bin and a 2/8 chance in the second one. And if I simplify that down, I would have that this would be 8/48, which would then simplify, can divide them both by 8, and this would be 1/6. So I've got a 1/6 chance of pulling two light bears. So first thing I'm going to do is continue calculating all these. So option C, now I'm looking at pulling the same color bear. That means that I could do a black and a black on the second one, or I could do a light on the first and a light on the second. So that means really that I have the probability of B1, the black on the first one, times the probability of black on the second one, plus probability of a light on the first one times the probability of a light on the second one. And those are both the values I just found. I found that when I multiply these, that if I go back a screen, that gave me 1/4. And I found that when I multiply these, if I go back a screen, I can see right there, that gives me 1/6. And if I add 1/4 plus 1/6, okay, I need my common denominator of 12s, and I would end up with 5/12. All right, so that leaves me with one last option to figure out, which is D. It says pull a different color bear from each bin. So that would be that the probability that I get a black on the first and a light on the second, or a light on the first and a black on the second. So if I think about that, that's the probability of black times the probability of light plus the probability of a light on the first, that's the probability of a black on the second. So that would be 2/6 times 2/8 plus 4/6 times 6/8. And this gives me 28/48, and that simplifies down to 7/12. Okay, so now I have my 4 probabilities for winning each of these games. So the last game has the best probability of winning, but then it's a matter of, well, what do I do when I compare the amount that I can win? So when I get to question 2, what I'm really looking at is this idea of what's the best game to play. The best game to play is the one where I can win the most money. So if I want to know where can I win the most money, I have to look at my expected values. So the expected value of A would be my probability of A, which if I go back, I found my probability to be 1/4. So I'm going to do 1/4 times the amount I could win, $16, minus the cost to play. And if I simplify that, I'm at negative $1. Not a good game. I'm losing $1 in the long run when I play. So now let's look at the expected value of game B. So I want to look at the probability again, come back here, was 1/6. So that's 1/6 times the amount I could win, which is $18, minus the $5 to play. Well, if I simplify that, that's negative $2. That's an even worse game to play. Even though I could win more, in the long run, I'd end up losing even more money. So let's check out game C. So here, game C, I go back to my probability of game C. I found it to be 5/12. So 5/12. Here I could win $15. And then I got to remember to subtract out the 5. Now this will give me a positive $1.25. So hey, here's a game I could finally win some money if I play. So I got to check my last game here, which would be game D. And in game D, if we go back, we saw that we had a probability of winning 7/12 out of the time. I'm only going to win $10. And then I subtract the 5. And here, when I do it, I end up with it coming out if I round to 83 cents. So I want to know which game is the best to play. It's the one that gives me the highest expected value, because in the long run, that one I should win the most. So in this case, I want to play option C. So while it wasn't the highest probability, the combination of the probability and the amount that could be won made it the best game to play.